Hello and welcome back, and if you are new here, welcome, we are very glad to have you here. In today's episode we will explain what is current gain in NPN and PNP BJT transistors. Okay, let's start with basics. These are the simplest schematics for NPN and PNP transistors. Firstly, we have biasing resistor RB, its function is to limit current going into base terminal of the transistor. Secondly, in addition to base current limiting function, it is also used to bias the transistor, or simply put, depending on its value and transistor parameters, it is used to drive the transistor into one of the three possible modes of work: cut-off mode or off-switch, amplifier, and saturation mode, or on-switch. Next, we have resistor RC, the collector current limiting resistor. Its function is to limit amount of current going into collector terminal of NPN transistor, or PNP transistor, respectively. This is the simplest transistor configuration, consisting only of transistor itself, two current limiting resistors and power source. These transistor configurations have no function. They do not perform any meaningful function in the circuit. They are primarily used for education purposes, to explain the roles of base and collector current limiting resistors. Because, if all of the parameters of the transistor, base current, base resistor, collector current, collector resistor and power source are all constants, base current, collector current, and emitter current are always the same. For NPN transistor, the emitter current is sum of base and collector current, and for PNP transistor the emitter current is difference between collector and base current. For both types of transistors, if base current and base resistor are constant, then the collector and emitter current remain constant. Again, we repeat, these schematics, where all parameters are constant, are primarily used for education purposes to explain the roles of base and collector current limiting resistors RB and RC, respectively. In this configuration, these schematics are equivalent to circuit consisting of power source and a resistor. The value of resistor is determined by desired value of emitter current and available power source. In order not to do disservice to our viewers, we are obligated to point out that this is idealized scenario, where operating temperature of transistor plays no role and all currents in the circuit are always constant. In real life, the ambient temperature of the circuit and operating temperature of the transistor, both plays role and have an impact at values of currents in the circuit and transistor. For significant increase in transistor temperature, there are also significant changes in value of base, emitter, and collector currents. Now here comes the part where things usually get confusing. The issue of current gain of the transistor. There are three terms in use when describing current gain: beta, hFE with capital FE, and hFE with small fe. Again, whoever is responsible for naming these parameters deserves a special place in hell. As if the transistors are not confusing enough, let's confuse the hell out of people even more with nonsensical nomenclature and symbols. Let's get our basic schematics back and try to make sense of this gobbledygook. For both NPN and PNP transistors, by definition, current gain is ratio between collector and base current. This parameter is supposed to tell us how much did transistor amplified base current. Now, this definition makes little or no sense at all, and here is why. In the first scenario, when transistor is in cut-off mode, acting as an off-switch, base, collector, and emitter current are all zero. So, ratio between collector and base current is also zero, if we disregard mathematical ban, that we cannot divide by zero. We digress. In this scenario, current gain is zero. Now, in the second scenario, when transistor is in saturation mode, or when it acts as an on switch, the ratio between collector and base current is determined by transistor parameters. We have a dedicated videos on this subject, episodes 11 and 12 of this series. In short, by reading transistor datasheet, we can obtain values for base and collector currents, determine proper values for base and collector resistors, and drive transistor in saturation mode. Transistor current gain in this situation is determined by transistor parameters and is constant. So, again, when we have constant values for base and collector current, their ratio is also constant, so there is really no point in determining ratio between constant values, as it will always be constant. In conclusion, when transistor acts as a switch, current gain parameter is meaningless. Now, the situation becomes clearer when the transistor is in amplification mode. We have learned from previous videos that in amplification mode, the collector current is proportional to base current. To put it simply, when base current goes up, so does the collector current. This next part is very important, so please pay attention. In an ideal situation, for an ideal transistor in amplification mode, linear increase in base current would produce linear increase in collector current, and their ratio would always be the same. In an ideal scenario, for any value of base current, the ratio between collector and base current would be the same. That ratio is called beta. This ideal transistor would have same amplification for any value of base current. To put it simply, for any value of base current, the ratio between collector and base current would be the same. Now, back to the real world. Here is where things get a bit more complicated. For the real-world transistors, linear increase in base current does not produce linear increase in collector current. For the real-world transistors, current gain, beta, is not constant for every value of base current. To make things more interesting, not only that beta changes in regards to base current, but also changes depending on value of power source used in transistor circuit. For the same base current, when using different power sources, the collector current changes as well. In real-world scenarios, beta is both base current and power source dependent. Let us put together a simple circuit using NPN transistor, variable power source VCC, variable base resistor RB, and for this, and only this occasion, we will omit collector current limiting resistor RC. In each of 10 scenarios, we will firstly set power source to 0.7, then 1, 1.5, 3.3, 5, 9, 12, 15, 24, and 30 volts. For each value of power source, we will vary the value of base resistor from 500 kiloohms down to 4000 ohms. These values are predetermined by transistor itself. Larger value than 500 kiloohms drives transistor in cutoff mode. Value of 4000 ohms for base resistor drives transistor in saturation mode, and any value less than 4000 ohms would burn out the transistor due to large current going into collector terminal. For each combination of VCC and base resistor, we will measure base and collector current and plot a graph for beta, the current gain of the transistor. The same exercise could be performed using PNP transistor. Before we continue with this video, can you recognize what this graph would be, if these lines were stacked one atop of the other? If you can recognize what this new graph would look like, please leave a comment in the comments section of this video. Now, let us get back to interpreting this graph. On horizontal axis are the values of base current limiting resistor, starting from 500 kiloohms, down to 4000 ohms. On vertical axis are values for beta. Each value is obtained by dividing measured collector and base current, for each combination of VCC and RB. Different color lines represent value for beta at a different VCC voltages. Blue for 0.7 volts, orange for 1 volt, and so on. The legend is placed at the top of the graph, depicting beta for each value of VCC. As we can see from the graph, values for beta varies widely for each combination of base and collector current. For example, when using VCC of 0.7 volts, the bottom blue line, value of beta logarithmically declines from 150 down to 75. In scenario where VCC equals 30 volts, beta logarithmically rises from 25 to over 200. It is important to notice that values for beta dramatically changes when base current is very small, very close to cutoff current, regardless of VCC. For the smallest change in base current, beta rises exponentially. As the base current rises, or to be more precise, when base current approaches saturation values, beta tends to be less volatile in its value. What is also very important to notice is that, there are very few ranges of base current where beta is almost constant. The most notable example of this is brown line, when VCC equals 15 volts, and RB resistor is in range between 350 and 150 kiloohms. So, what is the conclusion, regarding beta, the current gain for BJT transistors? Well, the conclusion is this: as current amplifier BJT transistors suck big time. Because beta is so volatile, and it is dependent on values for VCC and RB, the smallest changes in base current would cause uneven amplification of any signal. This causes distortion in signal amplification. One value of base current would be amplified 100 times, while next smallest increment in base current would be amplified 120 times, or more. This is unacceptable. We will deal with this issue more in one of the following videos, but for now, what you need to take from this is that current gain, beta, fluctuates widely depending on value of base current and value for power source. This makes any BJT transistor very poor current amplifier. Now that we know what beta is, let's tackle the issue of hFE with capital FE. What a delightful naming of parameter this is. So intuitive. For any given combination of VCC and RB, beta, or current gain, represents ratio of collector and base current. In transistor theory, this is utterly useless parameter. Its only usage is to be questioned in transistor exams. It has no practical usage whatsoever. Now, when we choose specific values for VCC, RB and RC, design and implement such circuit, then for that specific combination of circuit components, the ratio between collector and base current is called hFE, with capital FE. Please notice that there is no signal present for amplification. So, parameter hFE, with capital FE represents current gain for specific combination of components, when there is no input signal present, and transistor is in amplification mode of work. This hFE parameter, with capital FE, is also used in marketing, to falsely advertise current amplification of the transistor. Manufacturers choose specific values for base current and VCC, that produces the largest current gain hFE. In real life, these specific values have no practical implementation. For example, for most common types of NPN and PNP transistors, manufacturers advertise hFE gain of 250 or more, while using 10 microamps for base current, and 3 volts for VCC. This deceptive practice is common for all transistor manufacturers. They fine-tune and cherry-pick parameters to make their product stand out as one with highest current gain. Now, what is left is to define hFE, with small f parameter. Similar to hFE with capital FE, this parameter defines ratio between collector and base current, for specific combination of RB, RC and VCC, but now, when there is small current signal present at base input. This is also one very dubious parameter in transistor theory. What this small signal does, is that it turns current gain from hFE with capital FE to beta. The base current, determined by VCC and RB, adds together with variable current input signal and causes base current to fluctuates. We have learned that fluctuation in base current causes fluctuation in collector current, but fluctuations are not proportional, nor linear. Smallest fluctuation in base current causes beta to shift widely. When small current signal is present, the ratio between collector and base current is not constant, so this parameter changes widely, depending on value of sum of base current and small signal current. This parameter, also, has no practical usage. In conclusion, there are three parameters that refers to current gain in transistor circuits: beta, hFE with capital FE, and hFE with small fe. None of them have any practical use. By definition, current gain is ratio between collector and base current. Here is cheat sheet to summarize what we have learned in this video. Beta is current gain for any random values of RB, RC and VCC with no input signal present, when transistor is in amplification mode. Beta is not constant. hFE with capital FE is current gain of transistor for specific combination of RB, RC and VCC parameters, with no input signal present, and transistor is in amplification mode. hFE with capital FE is constant. This parameter is widely used to exaggerate amplification capabilities of the transistors. hFE with small fe is current gain of transistor when there is small input signal present at base terminal. This parameter is useless, as it fluctuates along with changes in base current. Once more, please allow us to extend season greetings and wish all of you a very happy new year. Please, before you leave, show your appreciation by liking this video, sharing it, leaving a comment, and consider subscribing to the channel. Thank you, and see you next time. Bye.